90% of machine learning projects never make it to production. Let that sink in. Your data scientists are building brilliant models. Your engineers are doing good work. But somewhere between the notebook and the real world, it falls apart. And that's not a talent problem. That's an MLOps problem. And most teams don't even know what they're missing. Hi, I'm Ross Webb, and I've led loads of data product teams and ML engineer teams with products at places like Amazon and Just Eat and many others. We've been building platforms used by thousands of professionals, and I've seen this failure pattern up close. Today, we're going to try to fix it. So welcome to MLOps Success, the show for ML engineers, data scientists, and product leaders who want to actually ship AI that works in production. Now, today we're going back to first principles, because if you're going to operate ML systems at scale, you need to understand what you're actually operating. And my guest today is Phillip Mortimer. Phillip is a computer scientist who until recently was chief scientist and CTO at a London fintech company building document intelligence systems. He's also been teaching MLOps at a university in France for over 5 years, and he's one of the only people doing that at a university level. And in this episode, Phillip will be walking us through the full MLOps lifecycle, data, models, deployment, monitoring, and then telling us why the whole game might be changing. Let's get into it.
Well, first of all, thank you very much for having me, Ross. Pleasure to be here. Yep, my name is Phillip Mortimer. I'm a computer scientist. I was until recently a chief scientist and CTO of a small financial technology company here in London, working on document intelligence, so trying to turn documents into structured data. And I also teach MLOps at Dauphine University in Paris. I've been a visiting lecturer there for the last 5 years, and I teach a course every year on MLOps. So the first thing to do is define MLOps and understand where it came from. There's lots of different ops in computer science. MLOps actually came from DevOps, so maybe I can talk briefly about DevOps first. So what is DevOps? DevOps is really kind of a mindset and a way of working in software development. The objective being to make sure your life as a software developer is not hell. That's kind of a high level, in a nutshell, definition of DevOps. So it's really about automating the process of software delivery to make it as seamless and as painless as possible. So that's things like planning your work before you begin, writing your code with following best practices, building your code automatically, running tests in your build pipeline, releasing it, versioning it, and deploying it to some hardware target, operating that code, and then monitoring that code as you operate it so that you know how well it's working, where things are going wrong, which will feed back into the beginning to the planning process so that you can improve your software continuously. So that's DevOps. So what is MLOps then? If we know what DevOps is, what is MLOps? Well, MLOps, of course, came out of DevOps. And there's a really great paper from Google, which was published in 2015, that's called Hidden Technical Debt in Machine Learning Systems. And in that paper, they talk about how in machine learning, you've got to worry about a lot more than just code. So the code can actually be really a very small part of the machine learning lifecycle. And you can write a code for a large language model with only a few hundred lines of code, actually. But you've got to worry about a lot of other things when you're doing machine learning. You've got to worry about your data, the infrastructure that you need to use, which is often a lot more complicated and specialized than in standard software development. You've got to worry about your model parameters, model hyperparameters. We'll talk a bit more about those later. Training runs. So there's a lot more to worry about in machine learning operations than there is in just standard DevOps, because that's where MLOps came from. And I like to think about MLOps in terms of a life cycle, similar to the DevOps life cycle. And there are 3 main parts to that life cycle. The first one is data preparation. The second one is model building. And the third one is model deployment.
That statistic about code being only a small part of the machine learning lifecycle, I want you to really sit with that. Most teams treat MLOps as a DevOps problem, but it's not. The data, the infrastructure, the hyperparameters, all of it needs to be managed. Philip's going to show us how.
In a nutshell, it came out of DevOps, but there's a lot more to machine learning systems than just code. So you need to worry about other things as well. Yeah, so it's a relatively new discipline. It's actually not taught very often, and the course I teach at Dauphine University is, I think, quite unusual. I don't think it's very commonly taught at university level. Most courses on AI machine learning focus on the theory, which is, I guess, the kind of the sexy stuff, so all the maths and what you can do with machine learning rather than how you do machine learning. But if the right mindset to have is someone who wants to automate things, someone who wants to organize their life and organize their work. I think that's a kind of important mentality to have, similar to DevOps. You want to be thinking, I could do it manually. It might take me longer to automate it at the beginning, but once I've automated it, I can then run it so much more quickly in the future. I can run it 100 times. I can run it 1,000 times because I've automated it. And then you move on to like the higher level problems, more interesting problems than the mechanics.
I love that point about getting past the mechanics so you can focus on the interesting stuff. If someone is listening to this and wants to rewire how they think about these systems, who are the thought leaders in the MLOps space that you look up to, or what resources do you recommend?
Thought leaders in MLOps. Well, there's Julian Simon, who was an AWS developer advocate. I'm not sure whether he still is, but he wrote a really great book on how to use Amazon SageMaker called Learn Amazon SageMaker. And then there's another nice book that I use when I'm teaching, which is Machine Learning Design Patterns. A bit old now, maybe 5 years old, but it talks about MLOps and how to think about machine learning in general. It's a great book. And then perhaps for more, think about beyond MLOps, if you want to think about LLM ops, then there's a really nice book from Paul Tan and Maxime Lebon called the LLM Engineer's Handbook, which was published last year.
I'll definitely be adding that handbook to my list. So we've got the mindset, we've got the resources. Now let's get into the actual execution. You mentioned the MLOps lifecycle has 3 distinct parts: data preparation, model building, and deployment. Let's start at the top. What goes into that first stage?
Yes, the MLOps lifecycle. So three important stages: data preparation, model building, and model deployment. Let's first talk about data preparation. So what does that involve and why is it important? Well, people say data is a new oil. Data is like the fuel of machine learning systems. So getting the right data and making sure the data is of good quality is a really important part of the machine learning lifecycle. So data preparation has a number of stages to it. There's exploratory data analysis, there's data annotation, and then there's data pipelines. So how do you transform your data from its raw format into a useful format for machine learning models? Let's start with exploratory data analysis. So first thing that you should do when you're looking at a data set is get to know it. Take a look at some examples, look at the type of the data, look at the distribution. Are there any duplicates? Does it have any biases? Are there any null values? So that's a kind of often forgotten but really important part of your data preparation stage. Well, first, look at your data really carefully, make sure you understand it, make sure you know what you're working with. And there are tools that you can use to do this. So you can just use a Jupyter notebook or a Databricks notebook, or I think most of the main cloud providers have got dedicated exploratory data solutions. Like on SageMaker, there's a data solution where you can even fit simple models to your data with a click of a button, which can give you some really important insights before you work on anything more serious and more hardcore. So exploratory data analysis, really important first step that's often forgotten. I think they fail to consider all the possible failure cases that you might have. So if they don't explore the data carefully enough, it could end up feeding bad data into the training pipeline. So garbage in, garbage out. And if you don't really look at your data properly, it's very easy to maintain garbage or not clean out the garbage from your data set before you start to use it for training. Maybe I can talk about the next stage of data preparation, which is data annotation. Yeah, data annotation. So in traditional machine learning, data annotation involves labeling the data that you've got with the kind of output that you want your model to generate. So if you're doing, say, machine vision, that will be perhaps if it's image classification, you might be labeling images as to whether they contain a cat or a dog or a sheep or something like that, or image segmentation, perhaps drawing a bounding box around objects on your image. If you're doing NLP, data annotation is kind of similar. Maybe you're annotating words, so tagging words either with part of speech for really old school ML learning, like nouns, verbs, adjectives, or perhaps labeling entities, people, places, institutions, or maybe even doing entity relations, so labeling relationships between different entities. And putting your MLOps hat on, the key thing to do when you're doing a data annotation is to use a dedicated tool. So there are a number of tools that can help you. There's open source tools like Label Studio, although they also have a managed version, and then Labelbox or V7 Labs, and then the main cloud providers also have their own data labeling solutions. And the reason that they're helpful is, one, they are designed for any possible labeling task that you can imagine. And two, they often have a kind of auto labeling solution. So they may have a simple model that trains itself in the background as you start to annotate. So once you start annotating your data, the simple model that's trained in the background will start making predictions, and then it becomes less of a data annotation, but more of a correction task. So it can really save you a lot of time. Sure, data pipelines. So once you've annotated your data, you often need to clean the data and prepare the data in a format that your model can understand. And the key thing to do here, if you want to do MLOps in the right way, is to make sure that that is a reproducible pipeline of operations. And tools that you might use here are things like Databricks, which is a very powerful solution built on top of Spark. It works with small data sets. It's very easy to use. You can just write Python or Spark code. But also it scales to absolutely enormous data sets given the power of Spark and its distributed computing model. So that's, I think, for really big training jobs, Databricks is becoming something of an industry standard. But if you've got a simpler task and a smaller data set, then you can use a simpler set of tools, maybe just a series of Python scripts, which you chain together with an orchestrator like Airflow or Dagster. And then once you've got that pipeline, which will take your raw data, clean the data, enrich the data, apply some transformation so it's ready for your model. When you add new data, you should then just be able to press a button and retrigger your pipeline so that it just runs seamlessly as you add new data. So it's reproducible and automated. Yeah, maybe I want to say one more thing before we move on from data preparation. Yeah, we're now in the world of LLMs, and you might think, do I need a data pipeline in the world of LLMs? Do I need data annotation in the world of LLMs? Because generally for LLMs, more data is better, right? So you might think, I'll just scrape as much data as possible and chuck it into my LLM. Scaling laws say that the more data you have and the more compute you have, the higher performance you get. And you may also think, I don't need data annotation either, because LLMs are trained using a self-supervised approach. So it's next token prediction. So you don't actually need to annotate your data at that stage. But actually, neither of those assumptions are true. So you definitely still need a data pipeline. Normally, the source of data for LLM pre-training is a massive corpus of data that's scraped from the web. And there's a lot of data cleaning that you need to do to make that data usable. So a lot of it is HTML. You need to extract the text from the HTML. You need to get rid of navigation bars from website, other information that's not relevant. And there's also a lot of duplication, which you'll need to remove. So sites which mirror other sites, and a lot of material that you actually want to exclude from your training set. So data cleaning, you might not want terror-related websites or adult material, anything unethical to be in your training data set. So data pipelines still relevant in LLM. And then data annotation, you also still need, because although you don't need it for the pre-training stage, you need it for the post-training stage where you're typically trying to evaluate the quality of an LLM's response and rank responses in terms of human preference, which then feed into post-training pipelines for LLMs. So all of these concepts are still relevant in the LLM world.
Well, here's where it gets ugly for a lot of teams. They skip EDA. They half-bake the annotation process, and then they wonder why their model underperforms in production. Philip's point about LLMs is critical. Everyone assumes LLMs make data work disappear. They don't. The problem just shifts. Now let's talk about actually building models the right way.
Yeah, model building. So model building is the second part of the machine learning lifecycle. So you've prepared your data and you want to train a model on that data. First thing I want to talk about is it's a cookbook from Andre Karpathy. I'm sure you know Andre. He's also got a fabulous YouTube channel, which I recommend you check out. And he published what he calls a training cookbook, which I think is really nice to think about when you're building your models. That cookbook has got 5 stages. Those stages are: become one with your data, fit a baseline, overfit, regularize, and squeeze out the juice. So let me go through those stages. So first one is become one with your data. I think we already talked about this, right? Actually, explore your data thoroughly, get to know it very, very well before you do anything. The second one is fit a baseline. So the first thing you should do when training a model is train a really simple model. Like if you're doing a classification task, just fit a logistic regression model. This will verify that your training pipeline is working properly and will give you like a baseline performance statistic that you can compare a more powerful model to. So that's fit a baseline. Third stage is a little bit counterintuitive. That is overfit. And normally overfitting is a bad thing in machine learning, but the idea of overfitting is once you've trained your baseline model, you will replace it with a large and powerful model with a huge number of parameters. And what you want to do is just take a few samples from your data set and make sure that you can overfit to those few samples. If you've got a model with many, many parameters and only very few data points, the model should be able to basically memorize those data points. And it's just a sense check. It's a sense check that your architecture will work and that you don't have any bugs or any problems in your training pipeline. Okay, then after that, regularize. So then throw in all the data. Try doing a full training run on the full set of data and see how that goes. And then finally, squeeze out the juice. So try all the tricks that you can think of to maximize model performance. So adjust your hyperparameters, use early stopping, train for longer, try an ensemble of models. Throw all the tricks that you've got in your back pocket and try and maximize the performance of your model. And I think that's kind of a nice framework to think about when you're building models. Maybe we can talk about more specifically the MLOps side, now that we know kind of roughly how to build a model. The first thing you want to do when you're building a model is choose the model architecture, but maybe that's self-evident. That's perhaps more of a research topic. So I'll assume that you've chosen your architecture already. The next thing you want to move on to is model training. So what is model training? Model training is a combination of different inputs that will generate an output artifact. Those inputs are your code, your data, the model parameters and how they're initialized, the hyperparameters. And for those listening who don't know what hyperparameters are, those are parameters that are set outside of your model training loop. Your compute, those are the inputs, and then the output is this model artifact. From an MLOps point of view, the key thing to do when you're training a model is to record all of these inputs using some MLOps software. Normally, you'd have a tracking server, an MLOps tracking server, where you can register all of this information. And then as training proceeds, you want to be registering performance statistics for your model to that tracking server. So things like the model loss, maybe F1 score, accuracy, area under curve, depends on all of these performance statistics differ depending on the type of model that you're performing. So the key thing from an MLOps point of view is to track these experiments. One training run is considered an experiment, and you need to track all of the inputs, track the performance of the model during the training, so that the output artifact, which will be your trained model weights, will have a proper lineage back to all of these input variables that were part of the model training. Does that make sense? Okay, so experiment tracking, super important in MLOps. Tools that you might want to use here are MLflow, which is open source from Databricks. And if you're using AWS, you can just deploy an MLflow server with one click, which is great. You can deploy it in one click on SageMaker. Yep. And that will give you a tracking server that you can use to send all of this information during model training. Weights and biases is another really common and popular choice, particularly in industry, but they have a kind of freemium model. So if you're doing a lot of experiments, you have to pay. But that's probably the gold standard of MLOps software. So weights and biases it's now owned by CoreWeave. So experiment tracking, super important. And then the output of an experiment, the output of a training run is this model artifact that I talked about, which is a set of model weights. It's a set of model weights and normally some metadata associated with your training run. And a really key concept here is that model artifact needs to be stored in what's called a model registry. So a model registry is another thing that will come with your MLOps software. It's a database to store all of your model training artifacts and version them and link them back to all that metadata that you generated during your training run. So you can see this model artifact has this loss score and this accuracy on my data set. And you will, when you've done a whole bunch of training runs, a whole bunch of experiments, you'll be able to pick the best model and know for sure that model is the one that you want to use in production. So that's a model registry. That's super important for model governance and model management. And then another concept that's really important here is documentation. And the standard documentation for a model is called a model card. Again, it comes from Google. Many things in machine learning come from Google. It was introduced in 2018 and is just a standardized piece of documentation regarding a model. And it will tell you things like the model architecture, what training data was used, the license, any ethical considerations, what performance that model has on particular tasks, who might want to use it, and what you might want to use it for. You've probably seen a model card if you've ever logged into Hugging Face and looked at one of their models. That's the documentation that you see on Hugging Face is an example of a model card. So that's model building. We had the Karpathy cookbook, tells you how to do it. And then if you want to automate it and manage it, you need to track your experiments, track your training runs, and register all the metadata associated with a training run to a tracking server. You need to register the model artifact that your training run produces in a model registry, and you need to add documentation to add a model card. That's how you do model building in an MLOps compliant way.
I've been banging the drum on experiment tracking for years. If you can't reproduce a training run, you can't govern it. You can't explain to stakeholders, you can't improve it reliably. The model registry and the model card. That's how you go from a science project to a production system. Now, you've built the model. Time to ship it.
Yeah, absolutely. So outside of an academic setting, training a model and demonstrating that it's highly accurate on some task is not very useful. Really, what you want to do with a model is use it to serve inference requests. As Steve Jobs said, real artists ship. And the same thing applies to machine learning. You want your model to have some return on investment. And normally that means deploying the model so that it can serve inference requests in production. And what does that mean? That means you send the model new data points and you ask it to make predictions and return those predictions to the user, who will then do something useful with them. So there are a few ways to do this. You could either have an embedded model. So if you're using your smartphone, maybe you've got a photo library on your smartphone, and these days you can search for people or objects in that photo library. But outside of Apple, Samsung, Google, and the likes, that's perhaps a little bit uncommon way to deploy your machine learning models. Mostly, machine learning models are deployed as a model as a service. So a model running in the cloud, which is exposed as an endpoint to which you send data, send requests for inference. The model will then make predictions and then return those predictions back over the network. So that's kind of the standard way of deploying machine learning models. Now let's bring some MLOps in. A really key consideration is to automate the deployment pipeline from the model registry that we talked about before to your server where you're going to be hosting the model. So you need to build an automated pipeline. You can actually normally trigger a deployment pipeline from your model registry. So perhaps there's an approve button in your model registry. When you hit the approve button, you should automate a pipeline to take the model artifact, and put it in something like a Docker container, and then host that Docker container on a server to serve inference requests. A really important consideration here is what kind of SLAs you have. So do you need super low latency or do you need low cost? And they will determine how you host that model. If you want very low latency, then probably you need to host it on a GPU server, but obviously that's more expensive. If you want medium latency and medium cost, then you might want to host your model on a CPU. And if you really want the lowest cost, then perhaps you don't want your predictions to be made in real time, and you can queue up your predictions and serve them in a batch process that maybe runs every hour or every day. So there's kind of trade-offs between cost and latency that you need to think about when you're serving models. And maybe I could talk a little bit about kind of the scaffolding that goes into a model server. So I talked about this model artifact, and you put that model artifact in a Docker container. So the Docker container needs to have the right runtime for your model. So let's say you trained your model in PyTorch, using PyTorch, then the Docker container that you're going to put your model weights in to serve inference requests, obviously also it needs to have PyTorch in it. So that's may sound obvious, but perhaps to some people it might not be. And then the model server needs to do 4 things, basically. It's not complicated. When it starts up, it needs to load the model into memory. When it receives an inference request, so when it receives some new data, it needs to deserialize that request, apply whatever pre-processing is necessary to get the data in the right shape for the model. Then it needs to send that data, the pre-processed data, to the model to get a prediction, and then finally apply some post-processing to the model prediction, serialize it, and then send it back over the network to the client which made the request in the first place. So that's kind of like the mechanics of what's inside a model server. Yeah, one thing before we talk about model monitoring. So we're talking about model serving and how that works. You deploy it in the cloud. But a really important consideration is cost. So Amazon previously estimated, this is before the LLM boom, they previously estimated that 90% of the infrastructure cost related to machine learning is actually incurred during inference. That may be surprising some people these days when you hear about these LLM training runs, which cost billions of dollars. But historically, that's been the case. And I think that will be the case in the future again, when people start to think about monetizing these huge models that they're training. Most of the costs in machine learning should be in the inference stage. You want your model to have a positive ROI. It needs to make more money when you're using it to serve requests than it costs to train it. So inference optimization is a huge topic in MLOps. A few things you can do. You can have hardware optimizations, make sure that your hardware scales up and down automatically with demand. But perhaps more interestingly, there are software optimizations that are quite common when you're preparing a model for inference. And you have this, in machine learning, you have a kind of many-to-many problem between machine learning frameworks that you use to train models like PyTorch, TensorFlow, JAX, XGBoost, or whatever, and then different kind of hardware targets where you might deploy your model. That could be a GPU, could be a GPU from NVIDIA or AMD or someone else, could be a TPU from Google, or maybe a CPU. Even within CPU, you've got different architectures like ARM versus Intel. So typically what you would do is you would export your model from the framework that was used to train it, from PyTorch, to some kind of specialized format that's optimized for inference. So that'll be a lightweight runtime that is compiled for all of these different hardware targets, taking advantage of any hardware acceleration or optimizations that are available. So the kind of thing we're talking about here is ONNX, Open Neural Network Exchange. So that's quite an old one. Or these days, if you're talking about LLMs, things like llama.cpp or vLLM or TensorRT, which is NVIDIA's optimized serving solution. So these are kind of really lightweight but highly optimized runtimes that you use to minimize your costs of inference.
That stat deserves repeating. 90% of ML infrastructure cost in inference, not training, which means if you're not optimizing your serving layer, you're burning money every single day your model is live. Now let that sink in. And one more crucial piece, monitoring, because once you ship, the work isn't done.
Next one, you want to talk about model monitoring. Yeah. So once you've deployed your model and is serving requests with your DevOps/MLOps mindset, you need to be keeping an eye on what it's doing. So monitoring your model in production is really important. Typically for machine learning, that will be capturing both the input and the output. And that's really important because you need to make sure that the data that your model is receiving matches the distribution and shape of the data that you use for training. There's a concept called data drift, and often your data might change over time. Things, the world evolves, and your model may become out of date if you don't retrain it. This is the case with LLMs, where there's this concept of knowledge cutoff, but it was also a thing with traditional machine learning as well. Data drift happens, the distribution of your data changes over time. So typically what people would do there is capture perhaps a sample of input-output pairs while the model is running in production, and then feed those samples back into the beginning of the machine learning lifecycle, re-annotate the inputs, and use that as new data to retrain the model so that it maintains its relevance as the world evolves. And then you're back to the beginning of the machine learning lifecycle. So we talked about the whole machine learning lifecycle, data preparation, model building, model deployment. But actually today, people are using machine learning in a completely different way than they were 2 or 3 years ago. And actually now, the primary way that people interact with machine learning is by using someone else's model. So people are using LLMs and they're accessing them through an API. So most people who are involved in machine learning are not training models anymore. They're using someone else's model and are in the world of LLMs. So you've got a whole different set of consideration with LLM ops. And this is a slightly different field to machine learning engineering and ML ops. And there's actually a new name that's becoming the standard now. It's actually AI engineering. So people are building systems on top of someone else's machine learning. So it's much more of an engineering problem than an MLOps option, than an MLOps problem. one of the reasons why this is becoming so popular is because the models that you have access to from the likes of Anthropic and OpenAI and Google are so powerful that they are much better than a single task model, than a specialized model that you might train yourself with this traditional process of data annotation and model building and model training. They just have so much more context about how the world works, how language works, that you just don't get with this kind of single task model. So often taking a generative model, a generalized LLM that's not trained on any specific task, but asking it, giving it a prompt and giving it some instructions to perform the task that you want to do works a lot better than going through the whole process of training your own dedicated model on that task. So that's why LLM ops and AI engineering is the direction of travel for the field. And MLOps, I think, is becoming something that's perhaps only done in the big labs like Google, Anthropic, and OpenAI. And most people will be AI engineers working with models developed by other people. I am actually very excited by the whole concept of AI engineering. And I see that as the future. What I'm most excited about is agentic AI. And if you want to put an ops into that, it's agent ops. So how do you operate agents in production, which is another big topic in itself. But when I look at, say, the evolution of AI coding assistants, they've gone from a sophisticated autocomplete a couple of years ago to something that could write maybe a function or a class a year ago to this year with the addition of agentic coding, tools that can refactor a whole code base in one shot. And I think it's this adding the agent loop really is the big breakthrough here, because the model can then see the impact of its own actions. It gets feedback about its own generations. For example, it will write some code. It will then run the tests against that code. Because it's an agent, it can take actions, so it can run the tests. It will see that the tests fail, and then it can go back and iterate and fix the bugs in its own code. And it's this kind of feedback loop that you get with agentic AI that I think is super powerful and is the real breakthrough of 2025.
Now, let's land the plane. Philip gave us the complete MLOps lifecycle today, and here's what I want you to take from it. On infrastructure, data pipelines are not optional. Even in the world of LLMs, data quality and reproducibility are the foundation. Get your EDA in place before you write a single line of training code. And on delivery, experiment tracking is how you go from cowboy ML to production ML, MLflow, weights and biases, model registry, model card, non-negotiable. On business impact, 90% of your ML infrastructure spend is inference. That's where the ROI lives. That's where the optimization conversation needs to happen with your stakeholders. And on the future, if you're not thinking about agent ops right now, you're already behind. The teams that figure out how to operate AI agents in production are going to have an enormous advantage. So here's 4 next steps you can take, maybe even before next week. 1, pull up Google Hidden Technical Debt paper, read the intro. It will change how you see your ML systems. 2, if you're not tracking experiments, set up MLflow this week. It's free, it's open source. You can deploy it on SageMaker in 1 click. And 3, calculate what your inference costs are as a percentage of your total ML spend. I think that number might surprise you. 4, follow the brilliant Philip on LinkedIn. He's really awesome. And if this episode was useful, consider subscribing right now. There's a lot more coming. And drop a comment below. What's the biggest gap in your MLOps setup? I read every single comment. I'm Ross Webb. This is MLOps Success. See you next time. Bye for now.